Tonight, we're going to travel to the edge of our solar system, to a world you've almost certainly never thought about. A world so far from the sun that it receives less than 1,000th the sunlight that Earth does. A world predicted on paper before anyone ever saw it, with winds so fast they would shred apart anything we've ever built. But here's what's going to change how you think about our solar system. Neptune isn't just cold and distant and dark. It is, by almost every measure we have, the most violent place in the entire solar system. And by the end of tonight, you're going to understand how a planet the Sun has almost completely abandoned can somehow become the most catastrophic place in our solar system. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Neptune sits at the outer edge of our solar system, about 2.8 billion miles from the Sun at its closest approach. At its farthest, that distance stretches to about 2.9 billion miles. Earth orbits the Sun at about 93 million miles. Neptune is roughly 30 times farther from the Sun than Earth is. Light from the Sun takes about 8 minutes to reach Earth. It takes about 4 hours to reach Neptune. If you were standing on Neptune's cloud tops, looking back toward the Sun, you would see a star. Bright, yes, the brightest object in your sky by far, but just a star, a point of light. Not the blazing disk that dominates Earth's sky. Not something that warms your face when you step outside. Just a cold, distant point that provides almost no heat and almost no energy to the world around you. This is the first thing you need to understand about Neptune. Everything it does on its own. It doesn't have the sun to energize it. It doesn't have a nearby star to pump heat into its atmosphere. Whatever is driving the violence on Neptune, whatever is powering those impossible winds, is coming from inside the planet itself. That's what makes Neptune so extraordinary and so deeply strange. You can spend years thinking about Jupiter's storms, or Mars's dust seasons, or Venus's crushing atmosphere, and find plenty to occupy your mind. But every one of those planets has one thing in common. The Sun is nearby, delivering energy, driving weather, shaping the climate. Neptune doesn't have that luxury. Neptune is almost entirely on its own. And it has responded to that isolation by becoming the most meteorologically violent world we've ever found in our solar system. A world that shouldn't work the way it does. And yet here it is, doing exactly that, nearly 3 billion miles away. Neptune was the last planet in our solar system to be discovered, and the story of how it was found is one of the most remarkable achievements in the history of science. It begins not with a telescope, but with mathematics. In the early 1840s, astronomers had been tracking the orbit of Uranus for decades, and something wasn't right. Uranus wasn't exactly where the calculations said it should be. Its orbit was being perturbed, pulled slightly off course by something massive. Something whose gravitational influence was detectable, even if the object itself had never been seen. Two mathematicians, working independently and on opposite sides of the English Channel, realized what this meant. There had to be another planet out there. A planet beyond Uranus, massive enough to be tugging on it gravitationally, but so far away that no one had noticed it yet. In England, a young mathematician named John Couch Adams began working on the problem in 1843. He spent more than a year calculating where this unknown planet would have to be to produce the observed perturbations in Uranus's orbit. He was 24 years old. In France, a mathematician named Urbain Le Verrier was doing the same thing. He published his predictions in 1846. The predictions from both men were remarkably close to each other, and remarkably close to where Neptune would turn out to actually be. On the 23rd of September, 1846, the German astronomer Johann Gottfried Galle pointed his telescope toward the area of sky Leverrier had indicated. He found Neptune within less than 1 degree of the predicted position. 1 degree. Out of the 360 degrees of the entire night sky, Neptune was found on the very first night anyone looked for it. It was science at its most powerful. Pure reason predicting the existence of something no human eye had ever seen. Finding it exactly where mathematics said it would be. That has never stopped being extraordinary. And it's worth sitting with for a moment. The universe does not advertise everything it contains. There are things out there, massive things, that are completely invisible to casual observation. Things that only reveal themselves through the subtle influence they exert on objects we can see. Neptune was the first world we found that way. Noticed, not by looking, but by detecting the gravitational whisper it was leaving in the orbit of another planet. There was a controversy afterward about who deserved credit for the discovery. Adams had calculated his predictions first, but had struggled to get the British astronomical establishment to take his work seriously. Leverrier published first. Galle observed first. The British and French scientific communities engaged in a prolonged dispute about priority that got somewhat unpleasant and somewhat political. History has generally settled on giving both Adams and Leverrier shared credit. But Galle, who actually found the planet through the eyepiece, often gets somewhat less attention than he deserves. He's the one who actually saw it first. After the discovery, astronomers turned their attention to what this new planet actually was. Its size could be roughly estimated from how bright it appeared. Its distance was known from the calculations. Its mass could be estimated from how strongly it was pulling on Uranus. But the details would have to wait. For more than a century after its discovery, Neptune was essentially a point of light, occasionally showing faint hints of features, but fundamentally mysterious. We knew it was out there. We didn't really know what it was. What actually is Neptune? The answer, it turned out, was something completely unlike anything else in our solar system. Neptune is what astronomers call an ice giant. This is a category that needs some unpacking because the name is a little misleading. Neptune is not actually covered in ice the way you might imagine. It's not a frozen world with an icy surface. The term ice giant refers to the interior composition of the planet, and the word ice in this context means something different from the everyday meaning. Astronomers use the word ice to describe compounds made of hydrogen, oxygen, carbon, and nitrogen, specifically in their molecular forms: water, methane, and ammonia. These compounds are called ices, not necessarily because they're solid at room temperature, but because they condense from gas at lower temperatures than hydrogen and helium. Inside Neptune, at extreme pressures and temperatures, these compounds exist in forms unlike anything we encounter on Earth. Hot, dense, pressurized to an almost incomprehensible degree. Neptune is thought to have a small rocky core at its center, maybe 1 to 2 times the mass of Earth, surrounded by a vast mantle of these high-pressure ices, and then a thick outer atmosphere of hydrogen, helium, and methane. The mantle isn't solid. It isn't liquid in any familiar sense. It's a dense, hot, pressurized fluid that conducts electricity. The boundary between the mantle and the atmosphere isn't sharp. There's no surface on Neptune. You can't land on it. There's no ground to touch down on. The atmosphere just gets denser and denser as you descend until it grades into something that's more fluid than gas, and then into the pressurized mantle below. Neptune has a diameter of about 30,000 miles, almost 4 times wider than Earth. Its mass is just over 17 times Earth's mass. It's not as large as Jupiter or Saturn, which are gas giants, but it's significantly more massive than you might expect for its size, because the ices that dominate its interior are denser than the hydrogen and helium that dominate the gas giants. This is an ice giant's defining characteristic: more mass packed into a smaller volume. And that higher density has consequences for the pressures generated in the interior, which in turn affects the physics of what happens down there. The gas giants, Jupiter and Saturn, are mostly hydrogen. 90% or more of their mass is hydrogen and helium. The ices are a minor component. In Neptune, the ices dominate. Somewhere between 60 and 70% of Neptune's mass is water, methane, and ammonia in their various high-pressure forms. The hydrogen and helium atmosphere is just a thin outer shell compared to the vast icy interior beneath. This difference in composition is what separates ice giants from gas giants. And it's a difference that has profound consequences for everything from the magnetic field to the weather to the interior chemistry. The exact interior structure of Neptune remains one of planetary science's most pressing open problems. We know the outer layers reasonably well from Voyager 2's observations. We know the bulk density, and from that we can constrain what the interior must be made of. But the details of how the different layers are arranged, where exactly the transitions happen, what the pressure and temperature profile looks like as you descend from the cloud tops into the core, these things are still being debated and refined. What we can say with confidence is that the interior of Neptune is not like the interior of Earth. It is not like the interior of Jupiter. Ice giant interiors are their own category, governed by physics that we're still working to fully understand. To understand why Neptune is so violent, you first have to understand the energy problem. Earth's weather is driven by the sun. The sun heats the equatorial regions of Earth more than the poles. This temperature difference drives atmospheric circulation. Warm air rises at the equator, flows toward the poles at high altitude, cools down, descends, and flows back toward the equator near the surface. The rotation of Earth twists these flows into the complex patterns we call weather. Hurricanes, jet streams, trade winds. All of it ultimately powered by the sun's energy being unevenly distributed across Earth's surface. Neptune receives almost no energy from the sun. At 2.8 to 2.9 billion miles away, the sunlight that reaches Neptune is about 900 times weaker than what reaches Earth. 900 times. If you put a solar panel on Neptune that would power a house on Earth, it would barely light a dim bulb. The sun provides almost nothing to Neptune in terms of energy. And yet Neptune has the fastest winds of any planet in the solar system. Winds that routinely reach speeds of around 1,200 miles per hour. That number deserves a moment. The fastest surface wind ever measured on Earth was a 231 mile per hour gust at Mount Washington in New Hampshire in 1934. That's considered extraordinary. A once-in-a-century event. Neptune's winds are more than 5 times faster than that. And they don't stop. They're permanent features of the planet. Sustained, not gusts. An entire planet wrapped in winds that never drop below velocities that would be instantly lethal to any living thing. So where is all this energy coming from? The sun can't be the source. The numbers just don't work. The answer lies inside Neptune itself. Neptune generates about 2.6 times as much heat as it receives from the Sun. The planet has an internal heat source, the remnant warmth from its formation billions of years ago, slowly radiating outward through the planet and into the atmosphere. When Neptune formed, the process of assembly, billions of tons of material, slamming together under gravity, generated enormous amounts of heat. Gravitational potential energy converted into thermal energy. The planet has been slowly releasing that heat ever since. 4.5 billion years later, it's still releasing it. Still warm from its own birth. This is not unusual for the outer planets. Jupiter, Saturn, and Uranus all generate internal heat too. But Neptune generates proportionally far more internal heat relative to how little it receives from the Sun. Jupiter, for instance, also generates about twice the energy it receives from the Sun as internal heat. But Jupiter is also much closer to the Sun and receives far more solar energy to begin with. The ratio of internal to solar energy is less dramatic for Jupiter than for Neptune. For Neptune, the imbalance is extreme. Internal heat is the dominant energy source by a wide margin. And that imbalance is what drives everything. When you have a heat source deep inside a planet and almost nothing coming in from outside, you get an enormous vertical temperature gradient. Hot from below, cold from above. That gradient drives powerful convection. Material rises, spreads, cools, descends. And on a rotating planet, that convection gets organized into horizontal flows by the Coriolis effect. On Neptune, this process runs at a scale that has no parallel in our solar system. The vertical temperature difference is enormous. The planet is large enough to sustain massive flow structures. The rotation is fast enough to organize those flows into high-speed bands. And the result is winds that would be incomprehensible on any other world we know. This is actually something of a puzzle for planetary scientists, because Uranus and Neptune are so similar in so many ways. Both are ice giants. Both have broadly similar compositions. Both formed under similar conditions in the outer solar system. And yet, Uranus generates almost no excess internal heat. Its internal heat flux is so low that it barely exceeds what you'd expect just from the Sun's warming. Neptune, meanwhile, is pouring out 2.6 times the solar input as internal heat. Why the difference? We don't fully know. One hypothesis is that something in Uranus's interior creates a layer that inhibits the flow of heat from deep inside to the outer atmosphere. A thermal barrier of some kind, perhaps a compositional gradient at some depth, where the mixing of different materials creates a stable layer that convection can't easily penetrate. If there's a layer in Uranus that blocks its internal heat from reaching the surface, that heat would be trapped. Neptune, for whatever reason, doesn't have that layer, or has a less effective one, so its internal heat flows freely outward. That difference, seemingly small in terms of interior structure, results in one planet being the most windswept world in the solar system, and the other being comparatively calm. It's a lesson in how sensitive planetary outcomes are to relatively small differences in interior structure. Small differences in how a planet is built can have enormous consequences for what that planet becomes. Neptune's atmosphere is mostly hydrogen and helium at the top, similar to Jupiter and Saturn. But unlike those planets, Neptune also has a significant fraction of methane in its upper atmosphere. Methane absorbs red light and reflects blue light. This is why Neptune appears such a vivid, deep blue in images. It's one of the most striking colors of any planet in the solar system. That blue isn't surface coloring. There's no surface. It's the atmosphere itself. Billions of tons of methane gas absorbing the red end of the spectrum and reflecting the blue back out into space. Uranus also has methane in its atmosphere and should therefore also appear blue. And Uranus is blue. But it's a paler, more washed-out blue compared to Neptune's vivid, saturated azure. Why the color difference if both planets have methane? The best current explanation involves a haze layer in the upper atmosphere. Uranus appears to have a thicker layer of methane ice haze in its upper atmosphere than Neptune does. This haze layer sits above most of the absorption region and scatters light in a way that washes out the deep blue, making Uranus look paler and more cyan. Neptune's upper atmosphere has less of this haze, so the deep blue color from methane absorption is more visible. But why Neptune has less of this haze than Uranus, and what that tells us about how the two atmospheres differ, is still being actively studied. The vivid blue of Neptune is a color you can do chemistry from. When you look at that blue, you're not just seeing a pretty color. You're seeing evidence of the chemical composition of the upper atmosphere. You're seeing information about the haze layer and what it's made of. You're seeing the fingerprint of methane absorption encoded in light that has traveled nearly 3 billion miles to reach your eyes. Below those blue cloud tops, the atmosphere descends into heat and pressure that would be fatal to any spacecraft we've ever built. The cloud features visible in images sit at an altitude of about 30 to 40 miles above a deeper reference pressure level, roughly where the atmospheric pressure equals Earth's surface pressure. Below that, the atmosphere descends into conditions we've never directly sampled. The cloud features themselves are made primarily of methane ice. Crystals of frozen methane swept up into the upper atmosphere by the violent vertical motions below. Where these crystals catch the low sunlight, they cast shadows on the blue atmosphere below. Voyager 2 photographed those shadows. Thin streaks of darkness on Neptune's blue face. The shadow of a methane ice crystal falling on an atmosphere made of gas. It's one of the more quietly extraordinary images Voyager 2 returned. Higher up, there are thin hazes of hydrocarbons, chemical compounds created when methane in the upper atmosphere is broken apart by ultraviolet radiation from the sun, and the fragments reassemble into more complex molecules. Ethane, acetylene, and other hydrocarbons accumulate in a thin photochemical smog layer high in Neptune's atmosphere. It's the same basic process that creates smog in a city, just driven by sunlight rather than car exhaust. The chemistry of Neptune's upper atmosphere is actually quite rich, despite how cold and remote the planet is. Ultraviolet light is still arriving, even if faint. And it's enough to drive photochemistry, to break molecules apart and put them back together in new configurations. The atmosphere of Neptune is not a simple layered thing. It's a churning, dynamic system where chemistry and physics interact in ways we're still trying to fully understand. Each layer has different temperatures, different compositions, different wind speeds, and all of it is connected by those enormous vertical flows carrying heat from the interior upward toward the cloud tops. The temperature at the cloud top level is about minus 333 degrees Fahrenheit, or minus 203 degrees Celsius. That's cold by any standard. But as you descend into the atmosphere, the temperature rises rapidly. The pressure increases rapidly. By the time you've descended a few hundred miles, you're in conditions that make Venus look mild. And that enormous temperature difference between the cold cloud tops and the hot interior below is what drives everything. The atmosphere is essentially a heat engine, and Neptune is running it harder than any other planet in our solar system. The most famous feature in Neptune's atmosphere was first photographed in 1989 by the Voyager 2 spacecraft. It was called the Great Dark Spot, a massive, roughly oval-shaped storm system about the size of Earth, dark in color against the brighter blue of the surrounding atmosphere, rotating counterclockwise. A storm that, when Voyager 2 photographed it, appeared stable and persistent. Scientists initially compared it to Jupiter's Great Red Spot, which has persisted for at least 350 years and possibly much longer. They wondered if Neptune's Great Dark Spot might be equally permanent. It wasn't. When the Hubble Space Telescope turned its gaze to Neptune in 1994, just 5 years after Voyager 2's flyby, the Great Dark Spot was gone. Vanished. No longer there. In its place, on the opposite hemisphere of the planet, a new dark spot had appeared. This tells you something fundamental about Neptune. Even features large enough to swallow Earth whole are temporary here. A storm system that could contain our entire planet forms, grows, dominates the atmosphere for years, and then simply disappears. Not gradually fading. Not slowly dissipating over centuries, like Jupiter's storm might someday do. Gone within years. Neptune's atmosphere is so dynamic, so energetically violent, that it can create and destroy planetary-scale storm systems in what is, by geological or planetary standards, essentially the blink of an eye. Hubble has since detected multiple dark spots appearing and disappearing on Neptune over the years, each one forming in Neptune's southern hemisphere, drifting toward the equator, and then fading as it reaches lower latitudes. Astronomers using Hubble were actually able to observe the formation of a new dark spot in real time, watching it develop between 2018 and 2020. This was the first time humanity had ever caught a Neptunian dark spot in the act of forming. The observation revealed something unexpected about how these features form. The dark spot forms from below. Bright companion clouds appear first at high altitude, and then the dark spot develops beneath them as it rises from deeper in the atmosphere. The process takes months. Dark spots appear to be rotating vortices, columns of atmosphere spinning in place, driven by Neptune's extraordinary wind speeds and the complex pressure patterns they create. When they drift toward the equator, where the wind patterns are different, the pressure forces that maintain the vortex change. The vortex destabilizes, and the spot disappears. This is fundamentally different from what happens on Jupiter. Jupiter's Great Red Spot has been maintained for centuries, partly because of the stability of Jupiter's large-scale wind patterns. Jupiter's winds are banded, but the bands are relatively stable over long timescales. Neptune's wind patterns are so much more energetic, so much more variable, that nothing lasts at planetary scale. Everything gets swept away. Near the Great Dark Spot that Voyager 2 photographed, there was also a smaller, fast-moving feature. The imaging team nicknamed the Scooter. It was a small, bright cloud feature that raced around Neptune faster than the surrounding atmosphere, completing a full orbit around the planet in about 16 hours. Faster than any other cloud feature. It was zipping past the Great Dark Spot regularly, moving so quickly it appeared to be lapping the larger storm. What exactly the Scooter was is still not entirely clear. It may have been a convective plume, a column of material rising rapidly from deeper in the atmosphere. The kind of rising column that on a smaller scale produces a cumulus cloud on Earth. Scaled up to Neptunian proportions, fed by the enormous internal heat, moving at hundreds of miles per hour. The scooter was last seen during Voyager 2's flyby. Whether similar features exist today, we don't know. We don't have the observational capability to see features that small from Earth or from Earth orbit. Another mission to Neptune, spending years in orbit, could track features like the scooter across months and years. Could watch how they form and evolve. Could finally tell us whether they're rising convective columns or something else entirely. The wind bands on Neptune are among the fastest known atmospheric phenomena on any planet in the solar system. But what's particularly striking is how organized they are. On a planet this violent, you might expect chaos. Random swirls and turbulent eddies without any coherent structure. What Voyager 2 found instead was a highly organized banding system. Near Neptune's equator, the winds blow westward, against the planet's rotation direction. These are retrograde winds. At higher latitudes, moving toward the poles, the winds reverse and blow eastward in the direction of the planet's rotation. The fastest westward winds near the equator reach speeds of around 1,200 miles per hour. The differential between adjacent wind bands is extraordinary. Standing at the boundary between two of these bands, you would be exposed to wind shears that would tear apart any material structure we know how to build. The reason for this banding is the same reason Earth has trade winds and jet streams, just scaled up to a degree that makes Earth's weather look gentle by comparison. Neptune rotates relatively quickly, completing one rotation in about 16 hours and 6 minutes. The planet's rapid rotation organizes the convective flows from the interior into latitudinal bands. Material moving upward from the interior gets deflected by the Coriolis effect, which depends on latitude, and this deflection creates systematic east-west flow patterns that differ from one latitude band to the next. The result is those dramatic wind reversals you see in the data from Voyager 2. An atmosphere divided into zones of violently different wind regimes, butting up against each other with nothing to buffer the transition. There is a fundamental question about Neptune's wind system that we still haven't answered. How deep do the winds go? On Earth, wind is a near-surface phenomenon. It's driven by heating at or near the surface and is mostly confined to the lowest part of the atmosphere. On Neptune, there is no surface, so the winds could potentially extend deep into the planet. If they do, they're not just an atmospheric phenomenon. They're a planetary phenomenon. They're interacting with the interior. They may be linked to what's driving the magnetic field and the internal heat flow. If the winds are confined to a relatively thin outer shell, then the atmosphere and the interior are somewhat decoupled. The interior does its thing, pumps heat outward, and the atmosphere converts that heat into wind in a relatively shallow layer. If the winds extend deep, the whole system is more intimately connected. The wind profile with depth is one of the most important unmeasured quantities in planetary science right now. For the gas giants, we have some constraints from the gravitational data returned by the Juno mission to Jupiter. Jupiter's winds appear to extend down to a depth of about 1,800 miles or so. For Neptune, we have essentially no constraint. We don't know whether Neptune's 1,200 mile per hour surface winds are connected to winds at depth, or whether they exist only in the outer atmosphere. This question will remain unanswered until a probe is dropped into Neptune's atmosphere and measures the wind speed as a function of depth. That probe hasn't been built yet. It hasn't been funded yet. It might not fly for decades. But when it does, it will be one of the most important measurements in the history of planetary exploration. Deep inside Neptune, things become genuinely exotic. The mantle, the vast region between the rocky core and the outer atmosphere, is composed of those high-pressure ices, water, methane, and ammonia, at temperatures and pressures that are extremely difficult to reproduce in the laboratory. The pressure in Neptune's interior climbs to millions of times the atmospheric pressure at Earth's surface. At these conditions, the molecules that make up ordinary water, ice, and ammonia no longer behave anything like they do in familiar settings. Under millions of atmospheres of pressure, water can take on exotic forms that don't exist at the surface of any planet you're familiar with. One of the most fascinating possibilities for Neptune's interior involves diamonds. Methane, in Neptune's deep interior, subjected to enormous pressure and temperature, may decompose. The carbon atoms that make up methane can separate out under these conditions. And when carbon is subjected to extreme pressure, it doesn't just clump together. It crystallizes into the densest form of carbon we know. It forms diamonds, not small diamonds, potentially enormous diamond crystals forming deep in Neptune's interior under millions of atmospheres of pressure, sinking slowly toward the planet's core like a rain of precious stones falling through the pressurized fluid mantle. Laboratory experiments have confirmed that this process can work. Researchers have taken methane and compressed it under extreme conditions using laser-driven shock waves, achieving pressures of millions of atmospheres for brief fractions of a second, and watched it produce nanodiamond crystals. The conditions in these experiments are still far below what exists in Neptune's deep interior, but the physics is confirmed. Inside Neptune, diamonds may literally rain down toward the core. A diamond rain, falling through the interior of a planet nearly 3 billion miles away. It's one of those facts about the universe that sounds like it was invented for a science fiction novel. It isn't. It's what the physics predicts, and experiments have verified the mechanism. The diamonds wouldn't be accessible. They'd be buried under thousands of miles of pressurized fluid, heated to temperatures of thousands of degrees. But they're there. Somewhere in the interior of that blue world, falling in slow motion through the hot, dense fluid. As the carbon forms diamonds and they sink toward the core, a separate question arises about what happens to the remaining hydrogen. Under extreme pressures, hydrogen can undergo a phase transition into a form called metallic hydrogen, where the electrons are no longer bound to individual hydrogen nuclei, but can move freely between atoms. Metallic hydrogen conducts electricity like a metal. It's been observed in laboratory conditions, and it's thought to be abundant in the interiors of Jupiter and Saturn, where it contributes to those planets' powerful magnetic fields. In Neptune's mantle, the behavior of hydrogen at high pressures is part of what makes the electrical conductivity of the interior complex and highly variable with depth. And that electrical conductivity, driven by convection in the mantle, is what generates Neptune's magnetic field. That magnetic field, it turns out, is one of the most unusual things about the entire planet. Neptune's magnetic field is one of the strangest in the solar system, and understanding why it's strange tells us something critically important about the planet's interior. Earth's magnetic field is generated by convection of molten iron in the outer core. The rotation of Earth, combined with this convective motion, creates what's called a dynamo. The result is a magnetic field that is roughly dipolar. It has a north magnetic pole and a south magnetic pole, and the axis between them is tilted about 11 degrees relative to Earth's rotation axis. Not exactly aligned, but close. Jupiter and Saturn also have roughly dipolar magnetic fields, tilted only slightly from their rotation axes. Neptune's magnetic field is completely different. First, it's tilted 47 degrees from Neptune's rotation axis. Not 11 degrees. 47. This means the magnetic poles are wildly offset from the geographic poles. On Earth, a compass needle points roughly toward the geographic north. On Neptune, the equivalent would point somewhere dramatically different. Second, the magnetic field isn't centered on the planet. The center of Neptune's magnetic field is offset from the planet's center by about 55% of the planet's radius. The source of the magnetic field isn't at the core of the planet at all. It's off to one side, sitting more than halfway out from the center toward the surface. This creates a magnetic field that doesn't look anything like a simple dipole. It's complex and irregular, with multiple poles competing with each other. The result is that at Neptune's surface level, the magnetic field strength varies enormously depending on where you are. Some regions have magnetic fields many times stronger than the average. Other regions have fields much weaker. A spacecraft orbiting Neptune would be moving through regions of wildly varying field strength as the planet rotates beneath it. This unusual magnetic geometry tells us something crucial about where Neptune's dynamo is located. On Earth, the dynamo operates in the metallic iron outer core, deep inside the planet. On Neptune, the magnetic field geometry strongly suggests that the dynamo is operating not in the deep core, but in the mid-mantle, in the conducting, pressurized fluid of water and ammonia in the intermediate depths of the planet. This is called a thin-shell dynamo model. The conducting layer where convection drives the magnetic field generation is a shell at intermediate depth, not a core. One of the more exotic possibilities for Neptune's interior involves a state of matter called superionic water. Under extreme pressure and temperature, water molecules can enter a phase where the oxygen atoms form a rigid crystal lattice, while the hydrogen atoms flow freely through that lattice like a liquid. This phase, superionic water, is neither fully solid nor fully liquid. It's something in between. And because the hydrogen atoms are carrying positive charge as they move through the lattice, superionic water conducts electricity. If there's a layer of superionic water in Neptune's mantle, that layer could be contributing to the dynamo process in ways that are quite different from the iron core dynamo on Earth. The resulting magnetic field would be complex and non-dipolar, as we observe. Laboratory experiments have confirmed that superionic water exists. Researchers have compressed water to extreme pressures and temperatures and detected the characteristic properties of the superionic phase. It's real, and it may be filling a substantial portion of Neptune's mantle. The specific combination of a highly tilted, off-center magnetic field generated by a thin-shell dynamo in a superionic or highly compressed mantle is what makes Neptune's magnetosphere completely unlike anything else in the solar system. Uranus shares this general character, which is one reason why the ice giants are considered genuinely distinct from the gas giants. Something about ice giant interiors produces these exotic, wandering magnetic fields. What exactly is happening? How the dynamo works in detail, where the superionic layer begins and ends. how the complex magnetic topology evolves over time. These things remain open questions. And they will remain open until we send a spacecraft back. Voyager 2 launched on the 20th of August, 1977, almost 12 years before it reached Neptune. The spacecraft was designed for a grand tour of the outer solar system, taking advantage of a rare alignment of the outer planets that occurs roughly once every 175 years. Jupiter, Saturn, Uranus, and Neptune were all positioned such that a spacecraft could visit them sequentially, using the gravity of each planet to sling it toward the next. This alignment wouldn't occur again for the better part of 2 centuries. NASA recognized the window. Voyager 2 launched and spent 12 years threading between planets. Jupiter in July 1979. Saturn in August 1981. Uranus in January 1986. And then Neptune in August 1989. By the time Voyager 2 reached Neptune, it was traveling at roughly 12 miles per second. It would spend only a matter of hours in the vicinity of Neptune, swinging around the planet at closest approach, collecting as much data as its instruments could gather. And then, using Neptune's gravity one last time to fling it off into interstellar space. There was no second chance. No opportunity to slow down and enter orbit. No follow-up mission. The data it collected was all we would get for the foreseeable future. Before the flyby, we knew Neptune was there. We had rough estimates of its size and mass. We could see faint features with the best telescopes. But we had no detailed knowledge of its atmosphere, its rings, its moons, its magnetic field. The flyby transformed Neptune from a distant blue dot into a real world. One with storms and moons and rings, and a magnetic field that didn't obey the rules we'd learned from other planets. The images Voyager 2 sent back were unlike anything anyone expected. Vibrant blue, massive storm systems, high, cirrus-like clouds of methane ice casting shadows on the blue atmosphere below them. And those winds, those extraordinary, impossible winds. Voyager 2's closest approach to Neptune was about 3,000 miles above the cloud tops. At that distance, traveling at 12 miles per second, the encounter lasted only a few hours at closest approach. But the data returned was extraordinary in its density. Every instrument on board was running, pointed at the planet, recording as fast as it could. The radio science team used the way Neptune's gravity affected Voyager 2's trajectory to precisely measure the planet's mass. The magnetometer team was recording the magnetic field. The imaging team was capturing photographs with every available exposure. The plasma wave instrument was detecting charged particles. All of it happening simultaneously, in those few critical hours, while Voyager 2 swept through the inner Neptunian system at speeds no human-built object had ever reached before that point. The data was transmitted across nearly 3 billion miles of empty space. By the time the radio signals reached Earth, they were extraordinarily faint. The receiving dishes had to be among the most sensitive radio receivers ever built just to pick up the whispered transmissions. The entire scientific harvest of Neptune, humanity's only close look at this world, arrived as a trickle of radio signal across an almost incomprehensible distance. And then Voyager 2 moved on into the outer solar system, past the heliosphere, into interstellar space, and Neptune receded behind it, back into the dark. Triton deserves extended attention because in some ways it's even stranger than Neptune itself. Triton is Neptune's largest moon, It's about 1,600 miles across. That makes it smaller than Earth's moon, but still a substantial world in its own right. What makes Triton immediately unusual is its orbit. Every other large moon in the solar system orbits its planet in the prograde direction, the same direction the planet rotates. This makes sense because large moons form from the same rotating disk of material that formed the planet. Everything spins the same way. Triton orbits Neptune in the retrograde direction, backward, against Neptune's rotation. This is nearly certain proof that Triton did not form in orbit around Neptune. It formed somewhere else in the outer solar system, almost certainly as a Kuiper belt object, a large icy body orbiting the Sun in the cold outer reaches beyond Neptune's orbit. At some point in the early solar system, Triton's path brought it close enough to Neptune that the planet's gravity captured it. Capture of an object this large is extremely difficult to achieve through simple gravitational interaction. If Triton had approached Neptune, and there was no mechanism to rob it of orbital energy, it would have swung by Neptune on a hyperbolic trajectory and continued on its way. For Neptune to capture Triton, something had to rob Triton of enough energy to turn its solar orbit into an orbit around Neptune. The most accepted explanation involves a binary object encounter. Triton may have originally been part of a binary pair, two substantial objects orbiting each other as they drifted through the outer solar system together. When this binary pair encountered Neptune, the gravitational interaction could have split the pair, capturing Triton while ejecting its companion on a different trajectory. The ejected companion was effectively the price of Triton's capture. One object lost so that another could be gained. This is called the binary capture mechanism. The math works. The physics is consistent. But it required either an extraordinary coincidence or a much higher density of large outer solar system objects in the early solar system than we see today. Modern models of early solar system evolution do suggest the outer solar system was more densely populated in its early history. Objects that are now scattered or destroyed were once present in greater numbers. In that environment, binary encounters with Neptune might not have been as rare as they would be today. The consequences of Triton's capture for Neptune's original moon system were probably catastrophic. The original moons of Neptune, whatever they were, would have had their orbits destabilized by the arrival of a massive retrograde body. Gravitational interactions would have sent many of them spiraling inward to collide with the planet or be ejected entirely. What Neptune has today may be a completely restructured moon system, rebuilt after Triton's violent arrival. Now, Triton is the coldest measured object in the solar system. Surface temperatures reach about -391 degrees Fahrenheit, or -235 degrees Celsius. That's only about 38 degrees above absolute zero. At those temperatures, almost everything is frozen. Triton's surface is covered in nitrogen ice, carbon dioxide ice, methane ice, and carbon monoxide ice. The south polar cap is covered in a distinctive pinkish nitrogen ice, stained with complex organic molecules called tholins. Tholins form when ultraviolet radiation and charged particles break apart simple molecules like methane and nitrogen, and the fragments reassemble into longer, more complex organic compounds. They're reddish or brownish in color, and they appear on the surfaces of many objects in the outer solar system. Pluto has tholins. Titan has tholins in its atmosphere. They may represent a kind of organic chemistry that is widespread in the cold outer solar system, driven by radiation rather than heat. And yet, despite being 38 degrees above absolute zero, despite being coated in multiple layers of frozen gas, despite being one of the most frigid places in the entire solar system, Triton is geologically active. Voyager 2 photographed geysers erupting from Triton's surface. Not water geysers. Not the sulfurous eruptions of Io. Nitrogen geysers. Dark plumes of nitrogen gas shooting several miles above the surface, carried by the thin winds in Triton's trace nitrogen atmosphere. The mechanism involves sunlight, but barely. Even at Neptune's distance from the Sun, the faint sunlight is enough to penetrate Triton's transparent nitrogen ice layer and warm the slightly darker material beneath it. This warming, just a few degrees, is enough to vaporize some of the nitrogen ice from the bottom. The pressure builds. It builds until it finds a weakness in the overlying ice layer, and then it erupts. A geyser powered by sunlight so faint that the entire solar input at Neptune's distance is less than 1,000th of what Earth receives. The plumes from these geysers rise about 5 miles high and then drift downwind, depositing dark streaks on the surface. Voyager 2 photographed those streaks clearly. Dozens of them, all aligned in the same direction, showing that even Triton's near-vacuum atmosphere has a dominant wind direction. The geysers leave a record of their activity written in dark smears on a surface of pink and white ice. Triton also has what appears to be a relatively young, geologically resurfaced landscape. Large areas show relatively few impact craters, suggesting the surface has been renewed more recently in geological time. There may be cryovolcanism, the eruption not of molten rock, but of water and ammonia mixtures that are liquid in Triton's interior, but freeze when they reach the surface. The source of Triton's internal heat is likely tidal heating. Triton's retrograde orbit means it's slowly losing orbital energy to tidal interactions with Neptune. As that orbital energy is dissipated inside Triton in the form of tidal flexing, it heats the interior. This tidal heating may be keeping some portion of Triton's interior warm enough for geological processes to continue, even at temperatures that would freeze any material we're familiar with on Earth. And Triton is heading toward its end. The retrograde orbit means it will eventually reach the Roche limit, the distance at which Neptune's tidal forces become stronger than Triton's own self-gravity. When that happens, Neptune will pull Triton apart. The tidal forces will rip it into fragments, and those fragments will spread out into a ring, a spectacular ring. The debris from a world 1,600 miles across spread into a disk around Neptune. In roughly 3.5 billion years, Neptune will have rings that will put Saturn's current rings to shame. Not today. Not for billions of years. But the physics is already in motion. Triton is already on its way inward. The countdown has been running since the day it was captured. Neptune does have rings today, though they're nothing like Saturn's. They were suspected before Voyager 2's flyby, but not confirmed. Ground-based observers in the 1980s had detected what appeared to be partial rings, arcs of material rather than complete circles, which was a puzzling observation. If material is in orbit around a planet, why would it only occupy part of the orbit? Why wouldn't it spread out around the entire ring path over time? Voyager 2 solved the mystery. Neptune does have complete rings. 5 of them, named after individuals connected to Neptune's discovery and study. The innermost is the Galley ring, named after the astronomer who first observed Neptune. Then comes the Leverrier ring. Then the Lassell ring. Then the Arago ring. And then the outermost and most prominent, the Adams ring. But the rings are not uniformly dense. The Adams ring has regions where the material is much more concentrated than elsewhere. These clumps of denser material within the ring are what observers had been detecting from Earth. The ring arcs, named Liberté, Égalité, Fraternité, and Courage. The reason these arcs exist, why the material is clumped rather than spread uniformly around the ring, is still being studied. One explanation involves the gravitational influence of a small inner moon called Galatea. Galatea orbits just inside the Adams ring, and its gravity creates a pattern of resonances in the ring material. These resonances can act like gravitational corrals, confining material into clumps at certain locations around the ring. But the models don't fully reproduce the observed arc structure, and the arcs may not be as stable as they initially appeared. When Hubble observed Neptune's rings in 2023, using its near-infrared camera for the first time in decades, the images were striking. The Adams ring was clearly visible, along with other ring structures. The arcs were there, but they appeared to have evolved relative to what Voyager 2 had seen. Some arcs had shifted position. Some appeared fainter. Neptune's rings are not static. They're evolving on timescales of decades. And our best current models suggest the arcs in the Adams ring may eventually disperse as the resonance structure shifts over time. We may be seeing the rings in a relatively transient state. They might look quite different in a few hundred years. Or the arcs might persist for much longer. We don't know. What Hubble's 2023 images also showed in striking clarity was just how dark Neptune's rings are. They're made of material that reflects very little light. Dark organic compounds, probably including tholins and other carbon-rich materials, coat the ring particles. This is in stark contrast to Saturn's rings, which are bright white because they're made mostly of clean water ice. Neptune's rings are among the darkest material in the solar system. They absorb nearly all the light that falls on them, which is part of why they were so hard to detect from Earth in the first place. Neptune's other moons are a collection of small, mostly irregular objects. Most of them likely captured Kuiper Belt objects or fragments from the chaos of Triton's arrival. Neptune has 16 known moons in total. After Triton, the largest is Proteus, about 260 miles across, a dark, roughly equant object orbiting close to Neptune. Proteus was discovered by Voyager 2 in 1989. Before that, it simply wasn't visible from Earth. It's too small, too dark, and too close to the glare of Neptune to detect with ground-based telescopes. Even with Voyager 2, its surface features were only barely resolved. It appears to be an irregular, somewhat potato-shaped object with a large impact crater called Pharos that dominates one face. Nereid is another significant moon, discovered in 1949 from Earth. It was the second moon of Neptune known to astronomers for 40 years. But Nereid has one of the most elongated orbits of any known moon in the solar system. Its orbit is so elliptical that it takes it from about 860,000 miles from Neptune at closest approach to over 6 million miles at its farthest. An orbit this extreme is almost certainly the legacy of Triton's capture. Before Triton arrived, Nereid may have been a well-behaved, roughly circular orbit moon. The gravitational chaos of capturing an object the size of Triton likely reshaped Nereid's orbit dramatically, from stable to violently elliptical. One of the more interesting recent additions to the catalogue of Neptunian moons is Hippocamp. Found in 2013 by carefully analyzing archival Hubble images, Hippocamp is tiny, only about 20 miles across, orbiting close to Neptune, just outside the Adam's ring. What makes Hippocamp interesting is where it orbits. It sits very close to Proteus, in a region where you wouldn't expect a long-term stable orbit for an independently formed body. The best explanation is that Hippocamp is actually a fragment of Proteus. At some point in the past, a small impacting object struck Proteus hard enough to blast a chunk of it free into its own orbit. That chunk became Hippocamp. If that's right, then Hippocamp is a natural satellite formed not by gradual accretion from a disk, but by a catastrophic impact on another moon. A world that was literally born from a collision. A fragment of Neptune's larger moons, still circling the planet nearby. A tiny memorial to whatever struck Proteus all those years ago. The smaller, inner moons of Neptune are probably rubble. Fragments of larger bodies broken apart long ago. Some of them have irregular shapes and dark surfaces. They orbit close to Neptune, hugging the planet, subject to the complex gravitational environment near the rings. They're evidence of the violence that has shaped the Neptunian system across billions of years. Neptune sits at a boundary that is more significant than it might initially seem. Beyond its orbit, the solar system doesn't end. But it changes character fundamentally. The region beyond Neptune is called the Kuiper Belt, a vast disk of small icy bodies extending from roughly 30 astronomical units to about 50 astronomical units from the Sun. Neptune sits at almost exactly 30 astronomical units. Neptune's gravity defines the inner edge of the Kuiper Belt. The planet sweeps out a cleared region through its orbital path, and the resonant gravitational effects of its orbit structure, the Kuiper Belt, in complex ways. Objects that orbit the Sun in simple whole number ratios relative to Neptune's orbital period can be either stable or unstable, depending on the exact resonance. Pluto, for example, orbits the Sun twice. For every 3 times, Neptune completes an orbit. This 2 to 3 resonance with Neptune actually protects Pluto. It keeps Pluto from ever getting close to Neptune, despite the fact that Pluto's highly elliptical orbit does bring it inside Neptune's orbital radius at certain points. The gravitational resonance ensures that whenever Pluto is at its closest approach to the Sun, Neptune is nowhere nearby. Neptune is essentially the gravitational shepherd of the outer solar system. Its gravity has sculpted the Kuiper Belt, herded objects into resonances, cleared some regions, and populated others. The whole structure of the trans-Neptunian region, everything beyond Neptune's orbit, bears the imprint of Neptune's gravity. Triton itself was originally a Kuiper Belt object. Pluto and Eris and Makemake and Haumea are all Kuiper Belt objects. The outer reaches of our solar system are full of these icy bodies, and Neptune sits at the gateway to all of them. Its gravity is the dominant influence on everything in that outer zone. There are also objects in the Kuiper Belt that are in mean motion resonance with Neptune, but much farther out. The so-called scattered disk objects, bodies that have been gravitationally scattered by Neptune into highly elliptical orbits that take them far beyond the main Kuiper Belt. These objects carry the gravitational fingerprint of Neptune's influence. When you study the Kuiper Belt, You're studying the history of Neptune's gravitational influence on the outer solar system over 4.5 billion years, which makes it all the more remarkable that we know so little about Neptune itself. The most gravitationally influential planet for the structure of the outer solar system has been visited once, for a few hours, 35 years ago. There is also the question of what Neptune's existence tells us about the broader universe. When astronomers survey planetary systems around other stars, they find that planets in the Neptune mass and size range are extraordinarily common. More common than gas giants like Jupiter, more common than rocky planets like Earth. Neptune mass planets, ice giants, appear to be one of the standard products of planetary formation around other stars. We see them orbiting stars of different types, at different distances, in different configurations. Sometimes with multiple ice giant planets in the same system, sometimes alone, sometimes paired with smaller, rocky planets. The universe makes a lot of Neptunes. If you want to understand what most of the planets in the galaxy look like on the inside, what their interiors are composed of, how their atmospheres behave, how their magnetic fields are generated, you study Neptune. It's the nearest representative of the most common type of giant planet in the galaxy, and we have spent almost no time studying it up close. There's a practical problem here beyond just priority and funding. Neptune is far away, much farther than Jupiter or Saturn. A spacecraft taking a direct trajectory to Neptune requires many years of travel time, even with the most powerful rockets we have. To get there, in any reasonable time, you need gravity, assists, using the gravity of other planets to increase your speed. The planetary alignment that allowed Voyager 2 to do its grand tour was a once-in-a-century and three-quarters opportunity. The next time such an alignment occurs, current humans will long since be gone. Getting to Neptune today with a spacecraft that can carry useful science instruments and then slow down enough to enter orbit requires either a very long flight time or a very powerful propulsion system. Neither is cheap. Neither is easy. But the scientific return would be worth it. An orbiter, spending years circling Neptune, could revolutionize our understanding of ice giants, could answer questions about interior structure, magnetic field generation, atmospheric dynamics, ring stability, and Triton's geology that have been open since Voyager 2's brief flyby, could do for Neptune what the Cassini mission did for Saturn, transform it from a mystery into an understood world. The Planetary Science Decadal Survey of 2022 made its priorities clear. A mission to the ice giants was listed as the top priority, large flagship mission for the coming decade. The specific recommendation was for a Uranus orbiter and probe for a combination of scientific and practical reasons, involving the relative difficulty of reaching Uranus versus Neptune, and the windows of opportunity available in coming years. But the scientific questions it would address are directly relevant to Neptune. Understanding ice giant interiors. Understanding ice giant magnetic fields. Understanding how ice giants formed and how they shape the planetary systems they inhabit. A mission to Uranus won't answer all the questions about Neptune. Uranus and Neptune are different in important ways, as the contrast between their internal heat fluxes shows. But it would be the beginning. The first dedicated study of an ice giant from orbit. The first sustained observation of one of these worlds. And eventually, a Neptune mission should follow. A dedicated Neptune orbiter, with a probe to drop into the atmosphere and multiple flybys of Triton, could be one of the most scientifically productive missions in the history of planetary exploration. It would answer questions that have been open since 1846. It would tell us what's inside this planet. It would tell us why Triton has geysers. It would tell us whether the diamond rain model is correct. It would tell us how deep the winds go. It would tell us what the ring arcs actually are and whether they're stable. Every one of these is a question with implications that reach far beyond Neptune. Questions that matter for understanding the most common type of giant planet in the galaxy. When you step back and look at Neptune in its full context, what you see is a planet of extraordinary contrasts. It is the farthest major planet from the Sun, and yet it is the most energetically active in terms of atmospheric dynamics. It has the least solar input, and yet the fastest winds. It was the most recently discovered of the planets known to the ancients and the early modern era, found not by human eyes, but by human reason, and yet it remains the least understood. Its magnetic field is the strangest in the solar system, and its explanation lies in forms of matter that barely exist anywhere else in the universe. Its largest moon is a captured interloper from the outer solar system that is slowly spiraling to its own destruction. Its rings are dark as soot and structured by mechanisms we don't fully understand. Its interior may be raining diamonds, and none of this is speculation. These are the conclusions of serious planetary science. The diamond rain has been verified in principle in the laboratory. The unusual magnetic field is a measured fact. Triton's retrograde orbit is a certainty. The ring arcs are clearly visible in Hubble images. The internal heat flux is measured. The wind speeds are measured. The fact of the great dark spot forming and then disappearing is observed reality. This planet is genuinely extraordinary. It is doing things no other planet in our solar system does. It is doing them at the outer edge of our solar system, nearly 3 billion miles away, in the dark, without the sun's help. And we have visited it exactly once, for a few hours. More than 3 decades ago. The universe, as it turns out, does not give up its strangest secrets easily. Neptune's seasonal cycle is unlike anything in our familiar experience, and it has direct consequences for how the planet's atmosphere behaves over time. A Neptunian year lasts about 165 Earth years. That's not just a long year. It means that a single Neptunian season lasts roughly 40 years. For comparison, the entire span of time since Voyager 2 flew past Neptune has been less than one full Neptunian season. We photographed the planet during its southern summer. The South Pole was tilted toward the sun. The North Polar region was in the longest night in the solar system. 40 years of continuous darkness. Neptune's axial tilt is about 28 degrees, similar to Earth's 23.5 degrees. But because the year is so much longer, the consequences of that tilt are vastly amplified. On Earth, a single winter lasts a few months. On Neptune, the equivalent lasts 4 decades. During those 40 years of polar night, the atmospheric temperature in the polar region drops. The chemistry changes. Gases condense that might not condense elsewhere. Frost deposits can form on cloud particles. When the sun finally returns to that pole, after 40 years of absence, the warming starts. Chemistry that was suppressed in the cold begins to operate again. Cloud layers change their structure. The dark spot formation activity may vary with seasons. We don't know this for certain, because we've never observed Neptune through a full season. We've watched it for less than 40 years of Earth time. A single Neptunian season's worth of observation. Everything we know about Neptune comes from that one slice of its year. We've never seen it in spring. Never seen it in winter. We caught it in southern summer and have watched it slowly move towards southern autumn. That is the limit of our experience with this world. One season for one hemisphere. There is also evidence, from Hubble observations, that Neptune's south polar region has brightened over the years since Voyager 2's flyby. As that region approaches autumn and sunlight decreases, the atmospheric temperature at the South Pole has actually been rising. This seems counterintuitive. Less sunlight, leading to higher temperatures. But it's consistent with models that suggest the atmosphere takes decades to respond to changing solar illumination, and that what we're seeing now is the response to the solar peak from years earlier. The atmosphere is lagging behind the changes in solar input. This kind of delayed response is actually well understood in climate science. Earth's oceans have a thermal inertia that delays the response to seasonal changes. Neptune's deep atmosphere may have an even more extreme thermal inertia, taking decades to respond to changes in solar angle. Taking the full seasonal cycle of Neptune's atmosphere, how clouds and storms and temperature patterns change across a full 165-year orbit, remains completely uncharacterized. Understanding it would require either observations spanning multiple human lifetimes or an orbiter that could study the planet in detail over years and decades. We have the latter option. We've just chosen not to take it yet. The question of whether Neptune could ever be explored by humans is one that scientists and engineers have considered, not as a serious near-term proposal, but as a way of understanding the challenges of deep space exploration in general. Getting to Neptune is the first problem. The fastest spacecraft ever launched, New Horizons, which flew past Pluto in 2015, took about 9 years to reach Pluto's distance. Neptune's orbit is only slightly inside Pluto's average distance. A spacecraft launched directly to Neptune without gravity assists might take a decade or more. With well-planned gravity assists, transit time can be reduced. A mission that used Jupiter for a gravity assist could potentially reach Neptune in about 10 to 12 years. A human crew on such a journey would face every challenge that the generational ship concept faces for interstellar travel, just compressed into a solar system context. 10 to 12 years in a spacecraft, far from Earth, with no possibility of resupply or rescue. The radiation environment in the outer solar system is less severe than in interstellar space, but it's still significant. Beyond the protection of Earth's magnetic field, and farther from the Sun, the crew would be exposed to galactic cosmic rays and occasional solar energetic particle events for the entire duration of the journey. The psychological challenge of a decade of confinement would be extraordinary. The communication delay at Neptune's distance is about 4 hours one way, 8 hours round trip. Any conversation with Earth would require sending a message and waiting 8 hours for a response. The crew would be effectively isolated. They would need to make decisions independently, handle emergencies without help, and maintain their health, both physical and psychological, across years of isolation. And then there's the question of what they would do when they arrived. Neptune has no solid surface to land on. Even in orbit, the radiation environment and the complex magnetic field would make long-term habitation challenging. Any human presence near Neptune would likely be aboard a spacecraft in orbit, conducting observations. That's not nothing. The science of having humans there, able to make real-time decisions about observations, able to direct robotic probes, able to respond to discoveries as they happen, rather than waiting 8 hours for instructions from Earth, that has real value. But the cost in resources, risk, and human lives would be enormous compared to sending robotic missions. For now, and for the foreseeable future, Neptune remains robotic territory, an orbital mission with a probe dropped into the atmosphere. A flyby of Triton, remote sensing from orbit, building up a picture of the planet's structure and dynamics across months and years. That's the realistic science program for Neptune. It would be transformative. It would answer questions that have been open for decades. And it costs nothing close to what sending humans would cost. The formation of Neptune is itself a story of violence and displacement. In the standard model of planetary formation, planets grow from smaller bodies in a disk of gas and dust surrounding a young star. Rocky bodies collide and stick, building planetesimals. Planetesimals collide and build protoplanets. Protoplanets accumulate gas from the surrounding disk and become gas giants, or fail to accumulate much gas and become rocky planets or ice giants. The problem for Neptune is the timing. At Neptune's current distance from the Sun, the protoplanetary disk was sparse. There wasn't enough material out there to build a planet as massive as Neptune in the time available before the Sun's radiation blew the remaining disk gas away. The disk-clearing timescale is only a few million years. Neptune should have run out of building material long before it reached its current size. This is called the timescale problem for ice giant formation. The solution most planetary scientists now favor is that Neptune did not form where it is today. It formed much closer to the Sun. In the region where the protoplanetary disk was denser and more material was available. Then, at some point after the gas disk dissipated, dynamical interactions with the other giant planets caused Neptune to migrate outward. This is part of a broader scenario called the Nice model, after the city in France where it was developed in the early 2000s. In the Nice model, the giant planets, Jupiter, Saturn, Uranus, and Neptune, were initially packed more closely together in the inner part of what is now the outer solar system. Over millions of years, gravitational interactions between the giant planets and the disk of small icy bodies beyond them caused the planets to migrate. Jupiter moved slightly inward toward the Sun. Saturn, Uranus, and Neptune moved outward. At some point, Jupiter and Saturn crossed a mutual resonance, the 2-to-1 resonance, and this crossing sent gravitational shock waves through the system. Uranus and Neptune were flung outward, sometimes crossing each other's orbits until they settled into their current positions. This dynamical upheaval, if it happened, would have had massive consequences for the rest of the solar system. The Kuiper Belt would have been disrupted. Large numbers of comets and asteroids would have been sent on new trajectories, some of them toward the inner solar system. There is evidence in the impact record on the Moon that the inner solar system experienced an increased bombardment rate about 4 billion years ago, an event sometimes called the Late Heavy Bombardment. The Nice model's dynamical upheaval could explain this bombardment. The migration of the giant planets, particularly Neptune's outward migration, swept up vast numbers of small bodies and sent some of them raining inward toward the terrestrial planets. If this is right, then Neptune's migration was one of the most consequential events in the history of our solar system. Not just for Neptune itself, but for Earth. The bombardment that rained down on Earth during this period may have delivered significant amounts of water and other volatile compounds to our planet. The very oceans we live beside may owe their existence, at least in part, to the dynamical migration of Neptune billions of years ago. Neptune shaped the outer solar system. It may have shaped the inner solar system too. It may have played a role in making Earth habitable. That's a remarkable legacy for a planet that most people barely know the name of. One of the questions that Neptune raises is whether there are more undiscovered large bodies in the outer solar system. The story of Neptune's discovery, found because of its gravitational influence on Uranus, naturally leads to the question of whether something similar might be happening today. Are there any currently known planets being influenced by something we haven't found yet? The answer is complicated and somewhat controversial. There are anomalies in the orbits of some distant trans-Neptunian objects orbiting the Sun far beyond Neptune. Some of them have orbital orientations that appear to be clustered together in ways that seem statistically unlikely if they're arranged randomly. The clustering, if real, could indicate the gravitational influence of a large, undiscovered body far beyond Neptune. A body that some researchers have dubbed Planet 9 or Planet X, a hypothetical large planet orbiting the Sun at an extreme distance, perhaps several hundred to 1,000 astronomical units away. The evidence for this hypothetical planet is indirect and contested. Not everyone is convinced the orbital clustering is real. Statistical biases in how we detect and survey distant trans-Neptunian objects could produce apparent clustering even if no planet exists. Several large sky surveys have been searching for this hypothetical planet without finding it. If it exists, it's either very far away, very dim, or in a part of the sky that hasn't been well surveyed yet. The Vera Rubin Observatory, which began operations recently, may have the sensitivity to find this object if it exists. If Planet 9 turns out to be real, it would be the most significant planetary discovery since Neptune itself. A world far larger than Earth, orbiting at an enormous distance from the Sun, its gravitational fingerprint hidden in the subtle clustering of distant icy bodies. Found, as Neptune was, not by seeing it, but by inferring it from its effect on other objects. The mathematical hunting of an unseen world. It would be Neptune's discovery all over again, on a grander scale, more than a century and a half later. Whether Planet 9 exists is genuinely unknown. The evidence is tantalizing, but not conclusive. This is one of the most exciting open questions in solar system science. And the answer, when it comes, one way or another, will reshape our picture of our solar system's outer reaches. Triton's chemistry deserves more attention than it usually gets, because what's happening on Triton's surface may be relevant to questions about habitability far beyond our solar system. The surface of Triton is covered in a mixture of ices and complex organic compounds. The tholins that stain the polar cap pink are large, complex molecules, chains of carbon and nitrogen and hydrogen, assembled from simpler precursors by radiation. Similar chemistry occurs in laboratory experiments designed to simulate the surfaces and atmospheres of icy outer solar system bodies. Similar chemistry is thought to occur on Pluto, on Titan, on some Kuiper Belt objects. What's interesting about tholins is that they are, in a chemical sense, halfway between simple molecules and the complex organic compounds associated with biology. They're not biological, but they demonstrate that complex organic chemistry can proceed in environments far from the sun, far from liquid water, driven by radiation rather than heat. If you wanted to find the simplest possible preconditions for complex chemistry, Triton's surface is not obviously disqualified. The temperature is extreme. The energy flux is minimal, but the chemistry is there. And the question of what happens to tholins when they do encounter liquid water, which on Triton might occur briefly during any geothermal events, is chemically interesting. Laboratory experiments on tholin water mixtures show that some of the tholin compounds dissolve in water and react to form amino acids and other compounds relevant to biology. This does not mean there is life on Triton. It almost certainly isn't. But it illustrates that the organic chemistry happening in the cold outer solar system is not irrelevant to questions about where life might arise. The outer solar system may be a reservoir of organic chemistry that, given the right conditions, could become biologically interesting. We see analogues of this in the interiors of icy moons like Europa and Enceladus, where liquid water oceans exist beneath ice shells, potentially mixing with organic compounds from the ice above and chemical energy from hydrothermal vents below. Triton doesn't have a confirmed subsurface ocean, but with tidal heating providing internal warmth, the possibility that liquid water or ammonia water mixtures might exist at some depth below the surface is not absurd. We simply don't know. One of the measurements a future Triton lander could make is a seismic measurement, listening for moonquakes that would reveal the internal structure. Whether there's liquid beneath the ice. Whether there's geological activity deeper than the nitrogen geysers we can see from the surface. Whether Triton is truly inert beneath the frost line or hiding something warmer and more interesting in its deep interior. These are not idle questions. They connect to the fundamental issue of how common the conditions for liquid water might be in the outer solar system, and how common those conditions might be around other stars. Every world we explore teaches us something about what's possible. Triton, frozen and remote and going around backward, might turn out to teach us something important about the limits of habitability in the universe. The relationship between Neptune and our understanding of exoplanets deserves a fuller treatment. When astronomers first began discovering planets around other stars in the 1990s, they found a surprising abundance of large planets in close orbits, the so-called hot Jupiters. These were gas giants orbiting their stars at distances much closer than Mercury orbits our Sun, heated to extreme temperatures, whipping around their stars in just a few Earth days. These planets were surprising because we hadn't imagined that giant planets could form so close to their stars. We knew from our own solar system that giant planets form beyond the frost line, the distance from the star where water ice can exist, allowing them to accumulate the solid material needed to build their cores. In our solar system, the frost line is somewhere between Mars and Jupiter. All 4 giant planets form beyond it. As more exoplanets were discovered and survey techniques improved, it became clear that hot Jupiters are actually relatively rare. They're easy to find because they're large and in tight orbits that produce big, frequent signals. But they represent only a small fraction of all exoplanets. What's far more common, it turns out, are planets in the Neptune size and mass range. Sub-Neptunes, mini-Neptunes, and Neptune analogues show up constantly in planet surveys. The Kepler Space Telescope, which surveyed over 150,000 stars for transiting planets, found that small to medium-sized planets, from about 1.5 to 3.5 times Earth's radius, are the most common type of planet in the galaxy. Many of these planets fall in the size range between Earth and Neptune. They're called super-Earths if they're rocky, mini-Neptunes, if they have thick hydrogen and helium envelopes. And the boundary between the two categories is still being worked out. What we know from our own solar system is that Neptune is one archetype for these kinds of planets. Understanding Neptune's interior tells us about what these ubiquitous, medium-sized exoplanets might look like on the inside. Understanding Neptune's atmosphere tells us about what these planets' atmospheres might be like. Understanding Neptune's magnetic field gives us a framework for thinking about the magnetic environments of ice giant exoplanets. When you observe a transit of an exoplanet across its star, what you measure directly is the size of the planet and how it dims the star's light. From that, you can infer the radius. If you also have a radial velocity measurement or a transit timing variation, you can infer the mass. From the radius and mass together, you can calculate the bulk density. And, from the bulk density, combined with models of planetary composition, you can infer what the planet might be made of. If a planet has a bulk density consistent with being mostly water, methane, and ammonia, it's probably an ice giant. Probably looks something like Neptune on the inside. Understanding what Neptune looks like on the inside makes those inferences from distant exoplanet observations more reliable. The better we understand Neptune, the better we understand the most common type of planet in the galaxy. That's a strong scientific argument for studying it in detail. And it's an argument we've largely ignored for 35 years. There's something worth saying about the human experience of discovery, because Neptune's history offers an unusual perspective on it. We found it with reason before we found it with our eyes. That's rare in science. Most discoveries happen the other way around. You observe something, and then you reason about what it is. You look first, understand later. With Neptune, the sequence was inverted. Mathematicians reasoned from incomplete data, from the tiny perturbations in a neighboring planet's orbit, to the conclusion that something unknown must exist. They predicted its position. And then, only then, did anyone look. And it was there, exactly where the math said it would be. This sequence, reason first, observation second, confirmation third, is actually the gold standard for scientific prediction. It's the strongest possible test of a theory. Not just fitting data you already have, but predicting something you haven't yet seen. Neptune was a proof that mathematics is not just a human invention. It's a tool for discovering things that are real. Things that exist independently of us, billions of miles away in the dark. The fact that abstract equations could reach out across nearly 3 billion miles of space and point to a previously unknown world is still, if you really think about it, one of the more extraordinary things that science has ever demonstrated. There's a reason Einstein said that the most incomprehensible thing about the universe is that it is comprehensible. The universe follows laws. Mathematical laws. Laws that we can, with effort and ingenuity, discover and use to make predictions. Neptune's discovery was a demonstration of that in one of its most dramatic forms. A world found not by accident, not by systematic searching, but by pure logical inference from incomplete data. The discovery says something about mathematics, but it also says something about the universe. It says that the same laws we can write down on paper, laws derived from observing things on Earth, apply out there too, at 2.8 billion miles from the Sun, in the cold, dark. The same equations, the same physics, the same universe. That's not obvious. There's no logical necessity that a universe should work that way, but ours does. And Neptune is one of the cleanest demonstrations we have of that fact. Let me say something about what we don't know, because it's important to be honest about the limits of our understanding. We don't know exactly what Neptune's interior looks like. We have models. We have constraints from the bulk density, from the magnetic field geometry, from the heat flux. But the details of the interior structure, where exactly the different layers are, what phases the ices are in at different depths, whether there's a superionic layer and where it starts and ends, these things are uncertain. We don't know why Neptune generates so much more internal heat than Uranus. We have hypotheses. The thermal blocking layer idea has some appeal. But there's no consensus on the explanation, and it's possible the answer involves something we haven't thought of yet. We don't know exactly what drives the ring arcs. The Galatea resonance model is the leading explanation, but the details don't quite work out perfectly. And the arcs have changed since Voyager 2's observations in ways that aren't fully explained. We don't know the depth profile of Neptune's winds. This is actually one of the most pressing gaps in our knowledge of this planet, and it will remain a gap until we send a probe into the atmosphere. We don't know the surface geology of Triton in detail. We have Voyager 2 images from one hemisphere, taken during a brief flyby in southern summer. The other hemisphere is essentially unknown. The North Polar region, which was in 40 years of darkness during Voyager 2's flyby, has never been directly observed. We don't know whether Triton has a subsurface ocean. We don't know the detailed chemistry of its surface deposits. We don't know whether the geysers observed by Voyager 2 are still active. We don't know whether Neptune's observed cloud patterns change significantly with season. We don't know. That's an unusual admission in a science documentary. Usually the narrative goes, here's what we discovered, here's what it means. But Neptune is genuinely, profoundly underexplored. The gaps in our knowledge are as striking as the knowledge itself. And that should be understood as an invitation. An invitation to go back, to look more carefully, to send better instruments, to actually understand this world that has been orbiting our sun for 4.5 billion years, doing its extraordinary, violent, diamond raining, retrograde moon-captured, magnetic field-defying thing out there in the cold, mostly unobserved. The universe is patient. But the scientific questions don't wait forever. Every year that passes without a Neptune mission is another year of seasonal change unobserved, another year of ring arc evolution unmeasured, another year of Triton spiraling inward, orbit by orbit, with no one watching closely. Time, in the planetary science sense, is not unlimited. We should go back. Neptune's interaction with the solar wind is another dimension of the planet that rarely gets discussed, but reveals something important about the magnetosphere. The solar wind is a constant stream of charged particles, mostly protons and electrons, flowing outward from the sun at speeds of about 300 to 500 miles per second. It flows past every planet. By the time it reaches Neptune, it has thinned enormously. The solar wind particle density at Neptune's distance is only about 1% of what it is at Earth's distance. But it's still there. And it still interacts with Neptune's magnetic field in complex ways. At Earth, the interaction between the solar wind and the magnetic field creates a structure called the magnetosphere. The magnetic field deflects the solar wind, creating a cavity around the planet. On the sunward side, This cavity is compressed to about 10 Earth radii. On the night side, the magnetic field is stretched by the solar wind into a long tail extending millions of miles behind the planet. Neptune has a magnetosphere too. But because Neptune's magnetic field is so unusual, tilted at 47 degrees and offset from the center of the planet, the magnetosphere behaves in ways that have no analog anywhere else in the solar system. As Neptune rotates on its 16-hour day, the off-center magnetic field means that different parts of the magnetic field are alternately closer to and farther from the Sun. The magnetosphere wobbles. It changes shape over the course of a Neptunian day. The tail of the magnetosphere doesn't point smoothly away from the Sun. It corkscrews as the planet rotates. Within the magnetosphere, charged particles are trapped in radiation belts, regions where particles spiral back and forth along magnetic field lines. Earth has radiation belts, the Van Allen belts, which can damage satellites and are dangerous to humans. Neptune has radiation belts too, though, because of the weak solar wind at that distance and the unusual magnetic field geometry, they're structured differently from Earth's. Triton orbits within Neptune's magnetosphere. This means Triton is constantly exposed to the trapped charged particles in Neptune's radiation belts. Those particles bombard Triton's surface, breaking apart molecules and driving some of the chemistry that produces the tholins and other complex organic compounds on the surface. The magnetosphere connects Neptune to Triton in a physical sense. Particles trapped in the magnetic field modify the chemistry of the Moon's surface. The geysers on Triton may be ejecting material that gets carried along magnetic field lines and deposited elsewhere. The whole system, planet, magnetosphere, Moon, is dynamically interconnected in ways that we've barely begun to map. Voyager 2's magnetometer measurements during the flyby gave us a snapshot of this complex magnetosphere. A few hours of data as the spacecraft swept through. The current structure of the magnetosphere, how it changes with the solar wind conditions that vary over the solar cycle, how it responds to space weather events from the Sun. These things are essentially unknown. An orbiting spacecraft would be able to map the magnetosphere in detail over months, watching it evolve with Neptune's rotation, tracking changes in the radiation belt particle populations, monitoring how Triton's orbit sweeps through different magnetospheric regions. That's the kind of sustained observation that transforms a puzzle into an understood system. We don't have it yet. The polar regions of Neptune are among the most scientifically interesting parts of the planet and among the least well observed. Neptune's south pole has received more sunlight than any other part of the planet for the past few decades, because Neptune's axial tilt points the south pole toward the Sun during this part of its orbit. Since Voyager 2's flyby in 1989, Hubble Space Telescope observations have tracked changes in Neptune's south polar region. The south polar region has a distinctive appearance. It appears brighter than surrounding latitudes in certain wavelengths, suggesting different cloud composition or cloud altitude at the pole. There's evidence for a warm polar vortex, a region of warmer than average atmospheric temperature at the South Pole. On Earth, polar vortices are cold because poles receive less sunlight. On Neptune, the polar region that's currently in summer is warm, not because it's receiving more sunlight, which it is, but because the warming appears to reach higher into the atmosphere than would be expected from the dim sunlight alone. The internal heat plays a role here. The convective patterns that carry internal heat upward from the interior may converge at the poles in ways that amplify the warming from sunlight. The dynamical interaction between seasonal solar forcing and the constant upward flow of internal heat creates a polar climate unlike anything on Earth. In 2022, researchers using ground-based telescopes reported that Neptune's south polar temperature had actually dropped significantly over a period of just a few years. This was surprising. Based on the slow trend of solar heating during the approach of southern autumn, the temperature was expected to decrease slowly over decades. Instead, between 2018 and 2020, the south polar temperature dropped by about 17 degrees Fahrenheit, or about 9.5 degrees Celsius, in just a few years. Then, paradoxically, after this rapid cooling, a very warm vortex appeared at the South Pole, measuring temperatures dramatically higher than the surrounding atmosphere. The rapid cooling, followed by the extreme warm vortex, suggests that Neptune's atmosphere responds to seasonal forcing in ways that are much more complex and rapid than anyone expected. The simple models, where temperature changes follow slowly from the slow change in solar angle, are clearly not the whole story. There are feedback processes in Neptune's atmosphere that can produce large, rapid temperature swings at the poles. Understanding these processes is important not just for Neptune. The interaction between seasonal forcing and atmospheric dynamics is relevant to understanding climate on any planet with seasons. Neptune is an extreme case, with 40-year seasons and an atmosphere primarily driven by internal heat rather than solar input. But studying the extremes often teaches us about the underlying physics in ways that studying moderate cases doesn't. Neptune's polar climate, understood properly, would tell us something about atmospheric dynamics in a regime quite different from Earth's. And the knowledge transfers to understanding ice giant exoplanets, to understanding extreme climate scenarios on rocky planets. The universe runs experiments at a wider range of conditions than we can access in laboratories. Neptune is one of those experiments. The history of Neptunium, one of the radioactive elements, has a direct connection to Neptune. It's element 93 on the periodic table. It was the first transuranium element to be synthesized in a laboratory. Created in 1940 at the University of California, Berkeley, by Edwin Macmillan and Philip Abelson, who bombarded uranium with neutrons. The element was named after Neptune because it follows uranium in the periodic table, and in the solar system, Neptune follows Uranus. Uranium was named for Uranus. So, Neptunium was named for Neptune. Then came plutonium, element 94, named for Pluto. The outer planets stamping their identities onto the heaviest elements. Neptunium is highly radioactive. It doesn't exist naturally on Earth in significant quantities. When it's produced in nuclear reactors, it decays into other isotopes relatively quickly. The most stable isotope of neptunium, neptunium-237, has a half-life of about 2.1 million years. Long by human standards, short by the standards of Neptune itself, which has been orbiting the Sun for 4.5 billion years. The naming convention tells you something about how science builds on itself. Each new discovery in one domain gets connected to discoveries in others. Neptune, the planet, inspires the name of Neptunium, the element, which sits in the periodic table between two other planet-named elements. These connections matter not because they're scientifically profound, but because they're part of how human knowledge is organized and remembered. The name Neptune comes from the Roman deity of the sea. The planet was named for its vivid blue color, evocative of the ocean. The element was named for the planet. A chain of connections stretching from Roman mythology to quantum chemistry, with a blue ice giant somewhere in the middle. That's how knowledge accumulates. Not always in tidy, logical progressions. Sometimes in sideways connections, analogies, and naming choices that embed a discovery in the broader fabric of human understanding. Understanding the outer solar system has also required us to rethink what we mean by a planet. Neptune was considered the eighth planet from the Sun for decades after Pluto's discovery in 1930. For a while, Neptune was actually the outermost planet, because Pluto's highly elliptical orbit brings it inside Neptune's orbit for about 20 years out of every 248-year Pluto orbit. Pluto crossed inside Neptune's orbit in 1979 and remained there until 1999. During those 20 years, Neptune was technically the outermost planet. When Pluto dipped inside Neptune's orbit, it didn't mean the two were close. Their orbits are tilted relative to each other, and Pluto is protected from close encounters with Neptune by the gravitational resonance discussed earlier. But it did mean that the question of what constitutes the edge of the planetary zone was complicated. The reclassification of Pluto as a dwarf planet in 2006 by the International Astronomical Union put Neptune firmly back as the outermost major planet. The decision was controversial. Many people felt attached to Pluto as a planet, but scientifically, the reclassification made sense. Pluto is one of many similar-sized objects in the Kuiper Belt. It's the largest known one, but it's not qualitatively different from other large Kuiper Belt objects. Calling it a planet, while not calling Eris or Make planets, given that they have similar sizes, would be arbitrary. The definition the IAU settled on requires a planet to have cleared its orbital neighborhood of other similarly sized bodies. Neptune has done this. It dominates its region of the solar system gravitationally. Pluto has not done this. It shares its orbital zone with thousands of other Kuiper Belt objects. Neptune defines the boundary. Neptune is the last planet. Everything beyond its orbit is the domain of smaller bodies, scattered objects, and cold, dark ice. That boundary is not arbitrary. It's where Neptune's gravitational dominance ends and where a different regime begins. Standing at the boundary of the solar system's planetary zone. Orbiting in the dark. The final major world. It's worth pausing to think about what we have actually achieved in studying this planet, despite the limitations. We predicted Neptune's existence with mathematics before anyone saw it. We built a spacecraft in the 1970s, launched it in 1977, and guided it on a 12-year journey through the outer solar system using the gravity of 4 planets, arriving within a fraction of a degree of its intended flyby point at Neptune after more than 4 billion miles of travel. We received data transmitted from nearly 3 billion miles away, a whisper of radio signal arriving after more than 4 hours of travel at the speed of light, and extracted enough information from it to transform our understanding of the most distant planet in our solar system. We discovered its rings. We measured its magnetic field. We photographed its storms. We found its moons. We observed geysers on one of those moons in the coldest place we had ever visited. All of this from a spacecraft launched when pocket calculators were considered impressive technology. All of this from a flyby lasting hours. That is extraordinary. And then we took the data home, spent years analyzing it, published hundreds of papers, and largely moved on to other targets. Mercury, Mars, Jupiter, Saturn, comets, asteroids, all worthy targets, all studied in greater depth than Neptune has been. Neptune remains the one major planet in our solar system where we sent one mission, one time, and left. Not because Neptune isn't interesting. Clearly, it is. But because it's far, and going far is expensive, and we have limited resources, that trade-off is real. But it means that right now, if you asked what the most underexplored object in our solar system is, relative to its scientific importance, Neptune would have a strong claim to the title. The most violent planet. The least studied major planet. Both of those things are true. The next time you look up on a clear night, Neptune is out there. You won't see it without a telescope. It sits at the outer boundary of what we consider our solar system, nearly 3 billion miles away, moving slowly along its enormous orbit. One Neptunian year takes almost 165 Earth years to complete. Neptune was only discovered in 1846. It has not yet completed a single full orbit around the Sun since the moment we first laid eyes on it. We have only ever seen Neptune go partway around the Sun. Not once, all the way. When you hold that thought, the sense of scale becomes real in a way that numbers alone can't quite manage. We found this planet and named it and classified it and launched a spacecraft that took 12 years to reach it. And in all the time since we spotted it for the very first time, it has not yet made one complete lap around the Sun. That is how slowly Neptune moves. That is how vast this solar system is. And out there, in that vast cold dark, this blue world is doing what it has always done. Rotating in 16 hours. Generating heat from somewhere in its deep interior. Churning that heat into winds that would be unimaginable on Earth. Forming storms large enough to swallow our planet and then dissolving them within years. Raining diamonds through its pressurized mantle. Dragging Triton slowly inward, orbit by orbit, toward the day billions of years from now, when it will tear it apart and build something spectacular from the wreckage. That is Neptune. Violent and cold and blue and almost entirely unknown. A world we visited once, for a single afternoon, over 35 years ago. A world that has been turning and churning and doing all of this for 4.5 billion years without anyone watching. A world that is the most common type of planet in the galaxy, represented here at the edge of our own solar system, close enough to visit and yet so remote that we've barely touched it. The most violent planet in our solar system doesn't need us to validate its existence. It was there before our species evolved. It will be there long after the Sun has consumed our planet and grown cold. 3 billion miles away, spinning in 16 hours, pouring heat upward from its ancient interior, driving winds that never stop. It doesn't care whether we understand it. But we should try. Good night.